Okay, so, little class, my name is Professor Thames. Well, maybe not Professor, I'll call myself here Truman Thames, I suppose. So, what we're going to be going over today is the remainder theorem for polynomials, because, we also have remainders for integers and integer division, but we want to be focusing on the remainder theorem as it applies to polynomials. So, is everybody here kind of familiar with polynomial division, multiplication? You can add polynomials and stuff like that.
Sort of.
Okay, well, that's good, because we'll be going over polynomial division and whatnot. So, one example, I guess, to get started is going to be x minus 2 divided by, I guess I did use this one before. Okay. Divided by 3x to the 4th plus 7x cubed minus 4x squared minus x plus 11. So, how many times is x minus 2 going to 3x to the 4th? I guess it's okay if you respond at this time, but it's alright if you don't as well, because, this is just an example to kind of make sure you're acquainted with polynomial division, and we'll go over the remainder theorem after and have some kind of examples as well for you guys to engage in. So, I'm just going to kind of go through this one on my own, sort of, unless you have something you want to say. So, x minus 2 goes into 3x to the 4th, 3x cubed times, and we multiply 3x cubed times x minus 2, and we subtract that from our polynomial here, and with 3x to the 4th minus negative 2 times 3x cubed is 6x cubed. This cancels out. 7 minus 6 is 13, positive 13. X cubed to bring down to 4x squared. How many times is x minus 2 going to 13x cubed? It goes in 13x squared times. Multiply 13x squared times x minus 2. Subtract that from our polynomial. 13x cubed minus 2 times 13, 26x squared. Let's cancel out. Minus 4 minus 26. It's going to be 22x squared. Bring down minus x. How many times does x minus 2 go into 22x squared? It goes in 22x times. Again, we multiply our 22x by x minus 2. 22x squared minus 44x. This again cancels out. And minus x minus minus 44 is 43x plus 11. Let's bring down the 11, I guess I should say. And how many times does x minus 2 go into 43x plus 11? It goes in 43 times. Now, is that right? Have I done something wrong, or is that? Oh, no, yes, I just haven't continued the process. What am I doing? Minus 43 times x minus 2, 43x, minus 2 times 43 is 86. These cancel out. Plus 11 minus minus 86 is going to be 97. So our remainder is going to be 97. Now, what the remainder theorem for polynomials says is that if you have some polynomial like this one, and we divide it by some monomial like this one, with a constant term of minus 2, then we can do this to find the remainder, or we can just evaluate the polynomial at the opposite of this constant term here. So we can evaluate this polynomial at 2, and it will give us the remainder. So we can go through that right now. Let's take 3 to the 2 to the 4th, or times 2 to the 4th, plus 7 times 2 to the 3rd, minus 4 times 2 squared minus 2 plus 11. 2 to the 4th is 16 because it's 2 squared squared. 2 squared is 4. 4 squared is 16. So 3 times 16 plus 7 times 8 minus 4 times 4, which is 16 minus 2 plus 11. 3 times 16 is 48. 7 times 8 is 56. If we add those together, we'll do that after. Minus 16 minus 2 plus 11. Now we can just do 56 minus 16. We see the 6 is at the end. They make everything kind of nice because they cancel out to be 0. And then 5 minus 1 is 48. Okay. I'm just going to kind of do it straightforward because I don't want to get too confused. So 48 plus 40 is 88. 88 minus 2 plus 11. 88 minus 2 is 86. 86 plus 11. Did we do that before? Oh, no, yeah, we did. 11 is 86. 97. That did sound familiar. So you see we get the same remainder when we evaluate our polynomial at the opposite of our constant term here. We get 97, 97, and that's essentially what the remainder theorem for polynomials says. Now, what I want to do now is kind of explain how the algebra for that works out. So you can represent polynomials and the division process kind of with a simple-ish equation. So we know that for normal integer division, if we take our quotient times our divisor plus the remainder, we get our original number. So like n divided by d here would be q plus r over d. But if we're talking about polynomials, we generally talk about the polynomial as just p. That's p for polynomial instead of n for number, and p of x. And the rest is just other polynomials, because the remainder is going to be a polynomial, the divisor is going to be a polynomial, and the quotient is also going to be a polynomial. So our quotient polynomial times our divisor polynomial plus our remainder polynomial is our original polynomial. So the remainder theorem for polynomials says that if our d of x is just a monomial minus some constant, then p evaluated at a equals the remainder. And this is because d, or p equals this, and d at a is going to be a minus a, which is just going to be 0. So d of a equals 0. So then p of a equals q of a times 0, which is just going to be just going to be 0. If we add it to r, it's just going to be the same as r of x, or r of a. We're saying r of a here because we're evaluating the whole thing at a. So we have to, anywhere we see x, we have to evaluate at a. So p of a equals r of a. But if we're dividing by a polynomial of degree 1, our remainder is going to be of degree 0. So this r of a is just going to be the remainder. The remainder is just going to be a constant term. Like in our example, we had 97 as our remainder. The remainder is always just going to be a constant if we're dividing by a polynomial of degree 1. So our polynomial evaluated at a equals our remainder. And that's a shortcut for finding the remainder. If you are on a problem on a test, and it says find the remainder of this polynomial divided by this polynomial, whether what you're dividing by is a monomial of degree 1, you can just evaluate at the opposite of your coefficient for the monomial, or the opposite of the constant term, not the coefficient. I guess it's kind of the coefficient of the constant term, but whatever. So what we're going to do now is you're going to walk me through an example of going through the remainder theorem process for finding the remainder of our polynomial, and then doing the long division way, so you can kind of get an example, get a feel for how much faster the remainder theorem lets you do things with the remainders for polynomials. So let's take some degree 3 polynomial, so it doesn't take too long. Let's take like 2x cubed minus x squared plus 3x minus 1. That seems reasonable. And we'll take like x plus 2. So what's the first step we're going to be doing here in doing our long division? We're going to be dividing this polynomial by this little guy here. So how many times does x go into 2x cubed?
2x.
Okay, so it's 2x squared times. And we multiply our 2x squared by x minus 2 and subtract it away from our polynomial here. So 2x squared times x plus 2.
2x squared plus 2, 4x cubed.
Well, 4x squared.
Squared.
It's 4x squared. And these cancel out, right?
Mm-hmm.
So then minus x squared minus 4x squared.
Negative 5x squared.
Negative 5x squared. And we bring down our next term plus 3x. And we want to know how many times x goes into minus 5x squared.
5x or minus 5.
Minus 5x times. So we multiply minus 5x times x plus 2. Subtract it away from this thing. Move over here. That makes more sense.
And we get minus 5x squared plus
5x squared. Oh yeah, that is minus. Ooh, I forgot about that minus there. But yeah, minus 5x squared. And then minus 10x, yes. So minus 5x squared minus well, obviously these are going to cancel out because minus 5x squared is 5x squared. And minus and positive cancel out. So we have 3x minus 10x.
so 13x.
Yes. 13x, bring down the minus 1. And how many times does x go into 13x?
13.
13 times. So, again, do a multiplication here. 13x. And then have 13 times 2.
26.
Okay, 26. These cancel out. Minus 1, minus 26. 27. So our remainder is 27. So now, we want to use the remainder theorem method, which should be much faster. And we want to evaluate this polynomial at the opposite of positive 2. So it's going to be evaluated at negative 2.
It gives you negative 27.
Yes, that is negative 27. Okay. Now, we're evaluating this polynomial at negative 2. So we have 2, negative 2 cubed minus negative 2 squared. It's going to continue on the next line. Plus 3 times negative 2 minus 1. So this first term is, well, negative 2 cubed, so it's a negative 2 squared times another negative 2. So negative 2 squared is 4, and 4 times negative 2 is
8.
so negative 8 times 2 is negative 16. And our next term, negative 2 squared, it's squared, so it's always going to be positive, yeah. It'll be 4, and then minus 4. And then plus 3 times negative 2,
Negative 6.
negative 6, and minus 1. So all these are nice and negative, so we just kind of think of it as addition, but then we know it's going to be negative at the end. So 16 plus 4 is 20, 20 plus 6 is 26, 26 plus 1 is 27, negative 27. Rightly lines up. So essentially that's how the remainder theorem can help you find a remainder of a polynomial if you know you're dividing by a polynomial of degree 1, and that's the only limitation. Yeah. So if you're dividing by a polynomial of degree 1, you can find the remainder of whatever you're dividing by. And that's essentially it. So are there any questions about?
I have a question.
Yeah.
So the remainder is negative. Is that due to the divisor being positive? So x plus 2, is that the reason? Or?
So it's negative, sort of, just because it turned out negative. I guess sort of the explanation would be that if you're multiplying this times this polynomial, it's going to get you almost to here, but then you're going to need to subtract 27 away. Mm-hmm. Like for polynomials, when you're finding the remainder, sometimes it's going to be positive, sometimes negative, and like when it's 0, you know it's an even dividend, or evenly divides. So it's similar to integer division, but like when you're dividing integers, your remainder is always going to be positive or 0. But in polynomials, it has a chance to be negative because the place values work differently. Like the place values are completely separate from each other. So like x cubed is not going to ever mess with the x squared term. So like if you have something off in the constant term, then you might have to subtract to get back to where the original polynomial was if you're working out the qx times dx plus rx equals px. Okay. So that's essentially sort of why you can go deeper into it if you really want to look into how polynomials act, because you can add, multiply, subtract, and divide polynomials just like integers, but they behave differently in some cases, and that's just one of the cases. Okay. So, that's pretty good.
What do you mean by behave?
They have different properties. So, for integers, if you're adding up the 1's value, eventually you get to a point where you carry on to the 10's value. In polynomials, that never happens. If you're talking about it like from degree 0 part to degree 1, if you're adding up 1 plus 26 plus 73, you're never going to get to anything that affects this next place value with the x term.
So they're kind of independent of each other?
Yeah.
And this is history? Math history?
History of math. So I'm not going into the history of polynomials. The history sort of deals with, they started off basically only using polynomials, quadratics as like solutions for geometric problems, but eventually they came to say like we can just do math with polynomials themselves, and they began to go into like cubics and quartics and degree whatever the heck instead of just degree 1 and 2. But that's kind of another kind of thing. But yeah, this kind of concludes our discussion on the remainder theorem and polynomial division. So thank you.